All right, everybody, we're back for Wednesday's lecture. Moving on with the oxygen dissociation curve today. A really fun lecture where we'll get to learn how to um, calculate AVO2 difference. So we'll get a little bit more into exercise and how this oxy-hemoglobin curve is related to your ability to exercise. So we'll do a quick little review. We'll get into that, and then we'll do the opposite side of oxygen uptake and oxygen utilization, move on to carbon dioxide transport. If we're moving oxygen to the muscles, that means we have to be moving carbon dioxide away from the muscles. And last, we'll talk about homework number 3 a little bit. Actually, we can just discuss that right now. You'll find that it's posted online. It is about a research article, a classic live high, train low article that's based on altitude training from 1997 from Ben Levine. Fantastic article. So the homework assignment is going to make you do something a little bit different. You're not just answering questions. That's the second part of it, but you'll see that most of the points of the 25 points for this homework are for the first part, which is called a graphical abstract. So what that is it's the purpose of it is for you to read the article, try and make sense of the article, and draw a picture or a series of pictures that depict kind of the main ideas of that. I'll post a couple examples of some great graphical abstracts later online as well. So the place you'd want to start with that is just by reading the article, getting a good kind of understanding of what's going on, what are they doing, and then moving from there. Okay, so let's move on. Let's do a quick little review of what we covered in the last lecture. Number 1, what are the time courses for increases in breathing frequency and tidal volume and their contributions to increases in pulmonary ventilation during exercise? So let's kind of start with the beginning here. Our pulmonary ventilation equals our tidal volume, the amount of air that's moving past your mouth per breath, times your breathing frequency. That's what we have to know first. And the question there is, how do each of these change when you start exercising? So let's think about this as early and late. We know overall when we start exercising, we have to increase the amount of air moving past our mouth into our lungs to enable us to increase our amount of oxygen transport to our muscles. But each of these different factors, tidal volume and breathing frequency, factor differently in there. Early, you're going to have your increase in tidal volume. And later, late stage, when you're moving towards exhaustion, is when you're going to get the increase in breathing frequency. So just remember, early, tidal volume goes up, late, breathing frequency. And if you haven't practiced this yet during one of your exercise sessions, I would really encourage you, start really slow, see what happens, understand that, okay, you're moving a little bit more than you would normally, so therefore your pulmonary volume has had to go up. So what's changed? Has your breathing frequency changed, or has your tidal volume changed? Then towards the end of your workout, I'd encourage you to try to go a little hard. Think about your breathing frequency then. Breathing frequency, you're going to notice is going to be a little bit higher. Okay. Number 2, how can you more accurately state the air is thinner at high altitude? What factor related to our atmosphere is related to this fact? Okay, so this goes back to my biggest pet peeve of people saying that there's less oxygen when you move to high altitude. And that is not true. A better way to say that the air is thinner is the air is less dense. Okay, the column of air that's sitting on top of the air that you're breathing at low altitude is going to be bigger than the column of air sitting on top of the air that you're breathing. So let's say, for example, that this green bar right here is the air that you're breathing. At the high altitude, the pressure on top of that air that you're breathing is less. Therefore, that's going to allow that air that you're breathing to expand. Okay, less pressure equals more volume. If there's more volume, with the same amount of stuff in it, it's less dense. And if it's less dense, that means those oxygen molecules are further apart. Are there fewer oxygen molecules as a percentage-wise? Absolutely not. Same percent O2, but just less ppO2, which is the partial pressure of oxygen. Okay, really, really important to remember that differentiation. Number 3, What are the two compartments within our blood that transport oxygen from the lungs to work muscles? Let's start there, okay? Compartment number 1 is going to be blood plasma. Just like there's oxygen in lakes surrounding us because the column of air sitting above that lake is pushing the concentrations of all the gases in our air into that different medium, the same thing happens with our blood plasma. As our blood plasma moves past our lungs, the pressure of that oxygen sitting over the blood plasma is going to force some of that oxygen from the lungs, the alveoli, into that blood plasma. Okay, not very much though. Number 2 is our hemoglobin. And that's specifically on our red blood cells. And we know the second part of this question, which of these carries most of the oxygen? The answer to that is going to be hemoglobin. Remember, we figured out that blood plasma carries about 15 mLs, whereas our hemoglobin can carry over 1,000 mLs. So at any given time. So that's a really important differentiation for us to make for number 3 as part of our review. Number 4, what do we mean when we say that hemoglobin saturation has decreased? Okay, two-parter here. And then the second part, is that good or bad? When we say hemoglobin saturation has decreased, let's remember, let's draw our figure once more. Oops, not a line, I want a circle. There's our circle. That's our red blood cell. There's 1. There's 2. There's 3. Oops. 3. And 4. Okay, not exactly the best size, but overall what you can see there is that we have 4 hemoglobin subunits within our red blood cell. Okay, when we say it is saturated, okay, here's 1 oxygen, here's 2 oxygens, 3, whoops, 4 oxygens. So that is a 100% saturated molecule right there. Now, when we say that it is not saturated, that means we're losing. Let's make our eraser a little bit smaller so I can actually get to what I want to erase. Okay, now that oxygen molecule has moved off of there, out of there. There's a lower saturation. So as before, this red blood cell was 100% saturated. Now it is 75% saturated. Okay, that's what we mean when we say the hemoglobin saturation has decreased. Okay, so when we move from the alveoli or the aorta, leaving the heart where we have a lot of oxygen supply in that blood, to the exercising muscles, we're going to get a change in the saturation of oxygen on our red blood cells, on our hemoglobin subunits. Okay, it's going to go from about 98% saturated to about 70% if we're at low exercise intensity or at rest. So what that means is that a sum of those oxygen units from our red blood cells are going to be moving off, about 30%, okay, or about 28% if we start with 98% saturation. So what that means is 28% of those oxygen units are going to the muscle. So the last part of this question here, is this a good or bad thing? This depends. If your saturation went down at the lungs, that would be really bad. What we're seeing now, especially with this COVID-19 that's going around, is people are getting low oxygen saturation because they're getting pneumonia. The thing that's happening there is they don't have the ability to move the oxygen from their lungs into their blood. Their oxygen saturation is going down in their arteries, which is really bad. That's before it gets to the muscles. So if you have low saturation moving away from your lungs and away from your heart, that would be really, really bad. However, if you have low saturation at the muscles, that's a good thing because what that's saying is your muscles are extracting a lot of that oxygen off. So the answer to the second part of that, is this a good or bad thing? It depends on the location. Okay, so that finishes off where we were and kind of a review of our lecture from Monday. So let's move on. Here's our oxygen dissociation curve. The point of what we're going to be doing is we're going to be calculating the AVO2 difference. Now, Let's define what the AVO2 difference is first. That's arterial, venous, oxygen difference. Okay, go down the side there a little bit with my difference. So what we are doing is basically looking at the difference in oxygen content between the arteries and the veins. And the analogy I always use to describe this is, if you can remember back to your 21st birthday, okay? And before you go out for your 21st birthday, you go to the ATM, you take out $100, okay? You put that right in your wallet, and then your birthday celebration occurs. You wake up the next morning, you open your wallet, and you look in it, and you see that you have $50 in your wallet. So the question then is, how much money did you spend over the course of the night? You don't have a video showing you actually spending that money, and you can't go and interview all of the, the bookshops and, maybe the soda shops that you went into to get, celebration items for your birthday. You don't have video of that. You can't interview them. But what you do have is you have evidence of how much money you went into the night with, and you have evidence of how much money you came out of the evening with, and therefore you can say, okay, with pretty strong confidence, I guess I spent $50 on books and soda last night. Okay? A good, a reasonable amount of money to be spent on your birthday. Okay? 21st especially, it's a good one. So, the same thing happens with our ability to calculate AVO2 difference. If we know how much oxygen is moving in the arteries to the muscles, and we know how much oxygen is moving away from in the veins, away from the muscles, if we take the difference between the two of those, we basically say, well, that oxygen must have been used by the muscles. If that's the case, then we can calculate how much work has been done. We'll get to that a little bit later. So, the question here is, the only things that we are known is we know the pressure of oxygen in the artery, we know the pressure of oxygen in the vein, we know our hemoglobin concentration, and we know that we have an oxygen dissociation curve. Wow. So where do we start? Well, let's start with number one, the pressure of oxygen in the artery. So let's start with that. We'll do red. And if I make this a little bit bigger so you can see it, we say it's 100 millimeters of mercury. Here we are right here at 100 millimeters of mercury. Remember, partial pressure of oxygen, PO2, right there. Those two things match up. Let's see what happens. If we go to partial pressure of oxygen being 100 right to there, and then we draw our horizontal over. Whoops. Try again. Here we go. Okay. So we know that we have about 98% saturation. So 98% of our hemoglobin is saturated at 100 millimeters of mercury of pressure of oxygen. Let's move on to number two. We'll use some blue for this guy. Okay, pressure in the vein is 15 millimeters of mercury. Whoa, we are way down here. Let's make this bigger once again, just so you can see it. We'll draw our vertical. We'll draw our horizontal. What this tells us right here, we have about 15% saturation. So immediately, based on this information right here, you know that this person is exercising. We talked about these different partial pressures in the last lecture, and we know that normally we'd see something around 40 if that person was at rest, okay? But we're way down at 15, so we know that this person is exercising. Okay, so the next part of this is we know that the hemoglobin concentration of this person, we've taken a finger stick from them and used our HemoQ upstairs to determine what their hemoglobin concentration. You can do it through a different mechanism if you want to really use the spectrophotometer, okay? But we're just going to use the easy way. We're going to go with the HemoQ. All right, we determined that the hemoglobin is 15 grams per deciliter, and we also have our oxygen dissociation curve. So where do we start? Well, let's start with our math down here. Keep this picture in view. Number one, we know that our artery equals 98% and our vein equals 15% saturation. Number 2, we have to calculate what our maximal oxygen carrying capacity would be. Because we have what our saturations are right over here on our y-axis, but we don't know what the most is. If the most amount of oxygen we can carry is 10 milliliters, well, then we know we have 98 and 15% of that. Well, let's calculate how much we have. Max O2 carrying, put 2 R's in there, and to get that, we take our 15 grams of hemoglobin per 1 deciliter of blood. And from here, we are going to multiply this by our constant that we talked about last lecture. We know that each 1 gram of hemoglobin is capable of transporting, when fully saturated, all 4 subunits of all of those red blood cells in that gram, 1.34 mLs of O2. So that's going to give us 20.1 mLs of O2 per deciliter of blood at 100% saturation. Fantastic. So then step 3 is going to be to calculate how much oxygen is being transported in the arteries. In the arteries, that's going to equal our 0.98 times 20.1 mLs of O2 per deciliter of blood. And that will give us 19.7 mLs of O2. So as that blood is leaving in the arteries from the aorta, what we're seeing there is about, for every deciliter of blood that is moving out of that aorta, there is 19.7 mLs of O2 leaving in that deciliter of blood. Okay? And then if we go in the vein, this is your wallet the next morning, we're going to have 0.15 times 20.1 mLs of O2 per deciliter. And if we multiply those two things out right there, we get about 3.02 mLs of O2. If we subtract your step 4 right here, AV. Wait a minute. AV. O2 difference. We've calculated the amount of oxygen capacity. We've calculated the amount of oxygen that's in the arteries. We've calculated the amount of oxygen that's in the veins just by using our hemoglobin concentration. Now, if we subtract the amount in the veins from the amount that's in the arteries, then we get 19.7 minus 3.02. We'll just say 3 for the sake of this. We're going to get about 16.7 mLs of O2 equals our AVO2 difference. And that's going to be per deciliter of blood. So just by calculating from those 3 things and using our oxygen dissociation curve, from using our partial pressure of oxygen in the artery, our partial pressure of oxygen in the vein, our hemoglobin concentration, and using our curve right here, we can determine how much oxygen they lost. 16.7 mLs of O2 per deciliter of blood. That's how much currency is being spent in each amount of blood in this situation right here. So, we've talked about getting oxygen from the lungs to the muscles. Now we have to move on to carbon dioxide transport away. Let's see here. we're going to have kind of, we have 4 things listed up here, but I do this every year. I change 3 and 4 to 3A and 3B because those two are related very closely. All right, so let's think back to our methods of oxygen transport. We had 2 methods of oxygen transport before. We had dissolved in the blood plasma and bound to hemoglobin. And we have both of those same 2 mechanisms here with carbon dioxide transport. So number 1 is going to be about 7 to 10% of the CO2 produced within your contracting muscles is going to be dissolved in the blood plasma. So that's number 1. And number 2 is exactly the same. Remember, we talked about the Haldane effect last lecture, that when oxygen moves off, it's very easy for carbon dioxide to move on to those hemoglobin subunits. So about 20 to 30% of carbon dioxide is bound to our hemoglobin, okay? And a lot of times you'll see the equation carbon dioxide plus hemoglobin equals HbCO2, okay? And that's carboxyhemoglobin. Oops, not CO0. There we go. All right. So now 3A and 3B are through the use of my favorite buffer and yours, bicarbonate. Now, there are 2 ways that bicarbonate works. Our 3A up top is the slow way. And this takes place in the hemoglobin, okay? Or in the blood plasma, sorry. That's going to be our H2O plus CO2 is going to yield our H2CO3, which will then break down into HCO3 minus plus our hydrogen ion right there. And so you can see that we have our CO2 bound now as part of bicarbonate right in there. Fantastic. This also happens in a fast manner as well. Fast inside the red blood cell. And I'm going to give myself a little bit more room. H2O plus CO2. Exactly the same as before. This is going to move to our H2CO3, which is also known as carbonic acid. But the difference between this reaction right here and this reaction right here lies in what happens. If we want a reaction to go faster, all we need to do is add an enzyme. And the reason this reaction occurs quickly within the red blood cell and not in the blood plasma is because this enzyme only exists within the red blood cell, or has a higher concentration within the red blood cell. And that enzyme is going to be carbonic anhydrase. Carbonic anhydrase is going to catalyze the reaction of water plus carbon dioxide into our carbonic acid. And just like any other strong acid, we're going to get a dissociation. Here we go into our HCO3 minus. This is our bicarbonate. Right there, plus our hydrogen ion. Fantastic. So that gives you an example right there of our 4 ways or 3 ways, with one having 2 different options, of getting carbon dioxide from the muscles away into the blood and hopefully back to the lungs for us to breathe out. So if we take a look right down here, we have some great pictures of what this actually looks like. Here's our carbon dioxide moving from our tissues in the cell. And what's happening right here in part A of this is oxygen release and carbon dioxide pickup at the tissues. Okay? If we look at these two things together, so we know we want to get oxygen into the tissues, the cell. For what we're talking about here in exercise physiology, we're mostly talking about skeletal muscle cells. You can see that they have that little bit dissolved in the plasma. We have a small amount dissolved there. Okay, so after that oxygen moves off, the first thing that's going to happen is, here we go. This is right here. Let's see if we can do this in white. It might be a little bit easier. This is 2, right here. This is number 2. Our carbon dioxide plus our hemoglobin is going to make our carbaminohemoglobin, also known as carboxyhemoglobin, depending on what book you're reading. Okay, so if we go up to our list right up here, there it is. There's number 2. And here's our number 1. Right there. And you can see, if we compare the size of this arrow versus the size of this arrow down here for our oxygen that's dissolved, you can see that it's a little bit bigger, a little bit thicker arrow overall. That lets us know that a greater percentage of the total amount of carbon dioxide that's going to be transported in the blood is through it's being dissolved in the blood plasma versus our oxygen. So if we had to compare which molecule dissolves more readily into the blood plasma, our answer would be CO2 rather than oxygen. Okay, so there's our number 1 right there. Now, if we want to talk about 3A, that's this guy right here. Here's our slow combination of carbon dioxide and water into our carbonic acid, into our bicarbonate. Here's our hydrogen ion, which can bind to our plasma proteins, which act as that buffer. Okay? Now, here's our 3B right here. Carbon dioxide plus our water. Here is our carbonic anhydrase acting on that to form our carbonic acid. Carbonic acid then, just as we said before, transfers into our bicarbonate plus our hydrogen ions. However, what happens here is this bicarbonate has to then move outside of the cell. The problem with carbonic acid, or that bicarbonate, moving out of the red blood cell at that point is that it has a negative charge. You kind of have to zoom in really, really far. You can see HCO3 has a minus charge. Our hydrogen ion has that positive charge. When that negative charge leaves the red blood cell, we have to make sure that we maintain neutrality within that red blood cell overall. So therefore, we have chloride moving in. And this is known as the chloride shift. We have a transport protein on the red blood cell's surface that's going to allow that chloride to shift from outside the red blood cell to inside to help balance the charge. And what this enables us to do is continue to make our bicarbonate within the red blood cell and keep on shifting that bicarbonate out into the blood plasma. So we're taking advantage of the carbonic anhydrase that is inside that red blood cell, using it over and over again to move through a lot of carbon dioxide, bind it to our water, make some bicarbonate from it, and then we ship it out of the red blood cell so we can keep doing that. But in order to ship it out, we have to move a chloride in. Taking a negative charge out, we got to move a negative charge in. Okay, so those cover our 4 ways that we get our CO2 from the skeletal muscle into the red blood cell. Well, then what happens, the last part of this, is when we get to the alveoli. Here we are, alveoli. Alveolus is going to be 1 alveoli overall. Sorry, you can't quite see that. There you go. Alveolus. So now we are in the lungs. This blood is now deoxygenated, but is now moving back by an alveoli. And at this point, we have that low oxygen concentration overall. Remember, we started with 20.1 mLs of O2 per deciliter. Now, if we're exercising, this blood at this point is down to about 3 mLs of O2 per deciliter. So that's due to low hemoglobin saturation at this point. Okay, but now we're moving back by the lungs, and that's going to help us to be able to make more oxygenated hemoglobin. So what happens here? Well, just as before, we basically do the opposite. We're going to move that oxygen back on to the hemoglobin. We're going to also dissolve a little bit more oxygen here. At this point, because the CO2 concentration, okay, let's think about this. CO2 concentration here is very high. CO2 concentration here is very, very low. In this case, when we're in the tissues, skeletal muscle, our carbon dioxide is going to move down its concentration and pressure gradient from the tissues where we're producing a lot of carbon dioxide into the blood where there's not that much. Then, when we move back to the lungs in the alveoli, now our carbon dioxide concentration here in the lungs is very low overall. Our carbon dioxide concentration here is relatively high. So now we're going to move down our pressure gradient once again. Our carbon dioxide is going to come out of solution. Basically, what you can think of this as, you're taking the top off your soda. If you're taking the top off your soda, when those carbon dioxides are in solution, the pressure is equalized between the air above your soda and the liquid underneath, that carbon dioxide is going to stay in solution. However, now at the lungs, you are basically taking the top off of that soda because you have room to move that carbon dioxide into the very, very low pressure of your lungs, which are connected to the rest of the atmosphere, where carbon dioxide pressure is relatively low in relation to your skeletal muscle, okay, where those contractions are taking place. Krebs cycle is producing a lot of carbon dioxide down there, okay? So if that concentration is very, very low and the pressure gradient is much different, all that carbon dioxide that was bound to bicarbonate and bound to hemoglobin is now going to move in the opposite direction. All the reactions that we showed up here moving in this direction, well, these are actually, if we wanted to be better about drawing these, what this reaction would actually look like, it would look like one of those arrows and one of those arrows. And the only reason, and same thing here, one of these arrows, one of those arrows. The only reason in the first part of this slide that we were showing our carbon dioxide move towards carbaminohemoglobin, our carboxyhemoglobin, are moving towards bicarbonate formation, is because there's low concentrations of those in reference to our skeletal muscle. There's a lot of carbon dioxide. We're going to move it into solution. Now, we have relatively high amounts of carbon dioxide in the red blood cells and relatively low amounts in our alveoli. So what are we going to do here? We're going to take this reaction and move it in the other direction. So all of that carbon dioxide that is bound and outside the cell right here, here we go. We're going to start with that bicarbonate that's outside the cell. We're going to move it back into the cell because that's where we have our carbonic anhydrase that can catalyze that reaction. As that HCO3 minus moves into the cell, guess what? We have the exact opposite of the chloride shift. So the chloride shift that happened in the first part of this to enable our bicarbonate to move out of the red blood cell is now doing the reverse. Now our chloride's moving out, and that can allow our bicarbonate to move in. We move back to our carbonic anhydrase right there, or to our carbonic acid, which can then be split into our carbon dioxide and our water. And that CO2 then moves in to the alveoli. Same thing down here. We used to be bound to our hemoglobin. When we move that hemoglobin, or when we move that carbon dioxide off, we have CO2 plus HB. Guess what? That oxygen is going to take advantage of that hemoglobin right there and then form our hemoglobin, our oxygenated hemoglobin right there. Okay. Last two. Here's this same bicarbonate up here, similar to this one. We're just going to do nice and slow transition into carbonic acid, nice and slow transition into H2O plus carbon dioxide, and that carbon dioxide can then move into the alveoli. This is just passive diffusion right here against the alveoli. That's why it's really important that alveoli has really, really thin membrane that protects it, because we want to be able to diffuse gases back and forth across that membrane very, very easily. Okay. Last one here, we have our carbon dioxide that's just simply dissolved in the blood plasma. Because it's dissolved in the blood plasma, it's going to move down its pressure gradient. Our partial pressure of carbon dioxide is higher on our blood side than it is on our alveoli side. So our carbon dioxide is going to move down its pressure gradient. And then we will start right over again at the very beginning and move everything back. So, yep, I think I've been able to cover this. If I wanted to make a point here, I would say that this one is our partial pressure of CO2 in the blood right outside the alveoli is about 100 millimeters of mercury. If we want to talk about within the alveoli, it's going to be about 4. Partial pressure of CO2 is going to be about 4 millimeters of mercury. So you can see by those numbers, 100 versus 4, that it's going to be very easy for this carbon dioxide to move out of the red blood cell, out of solution in blood plasma, and then into the alveoli. The last part here, we just want to answer one question before we finish up this lecture. What is the chloride shift? We've already kind of answered that, and all I would say here is the trading of a negative ion in chloride for another negative ion in bicarbonate inside and outside of the red blood cell. And the difference is this can go in both directions. Let's just draw this right here. Basically, they're just going to be trading with each other. If we're at the skeletal muscle when we want to bring a lot of carbon dioxide into the red blood cell, that's going to mean that we're going to be eventually kicking that carbon dioxide out of the red blood cell as part of bicarbonate, and therefore we're going to have to bring chloride in. Then if we're back at the lungs, we're going to be having to move that carbon dioxide out of solution through the red blood cell, and therefore we're bringing that bicarbonate, which is negatively charged, into the red blood cell, and therefore that chloride is going to move out. So that about covers our the rest of our oxygen dissociation curve, the rest of our carbon dioxide transport. We're going to be starting to move on to altitude on Friday. I'm hoping that all of our grades will be posted by the end of today. Josh and I have been working through these. If you have any questions at all on the exam grading, please get in touch with me. I'll be happy to go over grades by Zoom. I can do a quick little video conference with you if you have specific questions, or by email. So just let me know if you have any questions, and hopefully we can get those ironed out. Because, like I said, the final exam is going to be cumulative, so there will be some of these questions on there. So I want to make sure, if you have questions about the exam number 2, that we get it ironed out and straightened before we get to your final exam. Because the purpose there is to make you guys get the best grade you can on that final. All right? So that'll leave us for today, and I'll see you on Friday.